mentioned 1 and 2 on page 65. We'll come back to that one. But let's go ahead and let's go over 1 and 2 on your other page. So on page 71, you had 1 and 2 there as well. So number 1, state Boyle's law. So hopefully for that one, you found Boyle's law and you're able to write it out. Boyle's law is that a constant temperature for a given amount of gas, volume varies inversely with pressure. Think about what that means, but hopefully whenever you were going over your reading, you realized, okay, I kind of see where this was going now. Alright, and then number 2, state Charles' law. So Charles' law says the volume of a given amount of gas at a constant pressure is relatively proportional to absolute temperature. Alright, we'll talk about what that means a little bit later on, but so hopefully you wrote those 2 down. Alright, now let's go over the applications. Application number 1, convert 56 millimeters of mercury to torr and atmospheres. Alright, so if I have, for this first one, 56 millimeters of mercury, and I'm going to torrs, how many do I have? Now remember, what's the relationship between millimeters of mercury and torrs? Right, they're the same. So if I have 56 millimeters of mercury, that means I have 56 torrs as well. So they are equal. So this one is just more defined than this one. Not that we have 2 different units for it, but they are equal. So whatever I have of one, I have in the other one. The atmospheres is a little bit harder. So remember, how many millimeters of mercury are in an atmosphere? How many does it take to make up an atmosphere? Alright, well remember, if I have 1 ATM or 1 atmosphere, I have to have 760 torrs or millimeters of mercury. So 1 ATM equals that. So that means I need to take the 56 torrs, divide by 760, and that'll tell me which part of an atmosphere that I have. Because I don't have 760 torrs, I only have 56. So I don't have a whole ATM or atmospheric pressure, I only have part of one. So 56 divided by 760, you're going to get 0.0736. Lost my spot for a second. Now remember, this one has 2 sig figs and we divided, so that means this one must also have 2 sig figs, so it changes over into 0.074 ATM. So that is the answer for part A. Oops. So that is the answer for number 1. So how many torrs do we have and how many ATMs do we have? Alright, number 2. The sample of the gas is connected to an open-ended anemometer. So determine the pressure of each of the following situations. So I remember to draw one today, so that way you'll be able to visualize it. I'm going to shift this over a little bit so you can see it a little bit better. Okay, I think that works. Alright, so visualizing this one. So this one is an open-ended manometer. So if it's open-ended, that means that atmospheric pressure is pushing down on it. So I have the mercury on the inside, and the mercury is shifting one direction or the other. And so because of that, it'll tell me which one's stronger. If the atmosphere is stronger, it'll shift towards the gas. If the gas is stronger, it'll shift towards the atmospheric side. So let's look through that. Alright, so part A, the mercury level is 12 millimeters higher in the side open to the atmosphere. And the atmospheric pressure is 783 torrs. So the atmosphere is 783 torrs. So I'm going to write the battlefield. That's how much the atmosphere is pushing down. But my mercury, it says, is 12 millimeters higher. So if it's 12 millimeters higher, which one's winning if it's higher on the atmospheric side? The atmosphere or the gas? Hopefully you said gas. So okay, the gas is stronger than the atmosphere. So that means that is at least 783 torrs. But since the mercury has shifted 12 millimeters higher on that side, that means that I have to add them up together. So 12 millimeters of mercury. Now remember, I'm saying millimeters of mercury because that's what it gave. But remember, you don't have to convert like an actual practice from millimeters of mercury to torrs, as long as you remember, if I have 12 millimeters of mercury, I have 12 torrs as well. So you add up those 2 together and you get 795 torr. So that's the answer for this first part, so part A. So looking at the second part, I don't know if they gave you a different atmosphere. Yep, they did. Alright. So it says the mercury level is 37 millimeters higher on the side open in the gas. The atmospheric pressure is 759 torr. Okay, So it says the mercury level is 37 millimeters higher and the side open to the gas. So it's higher this direction. So which one's winning, the atmosphere or the gas? Atmosphere, because it's higher on the gas side. So that means that the gas is weaker than that. And so since it's shifted over 37 millimeters, that means I have to subtract it. So for this one, Unix converting, I subtract them and I end up with 722 torr. So that's the answer for letter B. Because you can tell it because the gas is shifted over to closer to the gas, so it's weaker. And then you also have to subtract how much it's shifted by, so 37 millimeters. Alright, the mercury level is 115 millimeters lower in the arm open to the gas. The atmospheric pressure is 1 atm. State the answer in atmospheres. This one's getting a little bit tricky now because they want to make sure that you know what you're doing. So the atmosphere is 1 atm. That means I'll have to convert later on. Since I can't measure atm and the shifting of the gas, so I'll have to convert this one. Alright, so it tells me the mercury level is 150 millimeters lower in the arm open to the gas. So that means that it's lower in the arm open to the gas. That means it's shifting that direction. So they're checking to make sure, are you thinking this through? So this one is shifting this direction. So if it's 150 millimeters lower in the arm open to the gas, which one's winning, the gas or the atmosphere? If it's lower in the side open to the gas. Right, the gas is winning. So that means I'm going to have to add eventually for it. So it says to state your answer in atmospheres. So we'll go ahead and we'll convert this to atmospheres. So if I have 115 torr, what do I need to do to go from torrs to atmospheres? Well, remember, if 1 atm equals 760 torr, that means if I have 115 torrs, I need to divide by 760 to figure out how many atms I have. So 115 divided by 760, that'll give me atms as a unit, so the torrs will cancel out. So 115 divided by 760, that'll give me 0.151 atms. So I'm going to need 3 sig figs eventually, so we'll just go ahead and just leave this as 3 sig figs. So since the gas is winning, I have to add these two up together. So 1 atm plus 0.151 atm all together. I think I messed up. Hang on. I did. Hang on. So your book points out the difference in mercury level is 150 millimeters. So what is the pressure of the atmosphere? What is the gas pressure? The atmospheric pressure is 750 torr. I wrote down the wrong thing. I went ahead and converted. I'm so sorry. So the atmosphere, I misread that. The atmosphere is 750. That's where I got my 115 from. So 750, and then for this one, so you add that. The difference between them is 115. So you add them up together. So 865. Sorry about that. Let me get my bearings straight really quick. I was combining both of them together, so I am sorry about that. So 715 torrs. I'm looking at number 3. I am so sorry. I completely done the wrong one. I was doing it right the first time. And I jumped down and I lost my spot. I'm sorry for all the confusion. So, number C, not number 3, because I jumped down halfway through. So it is 1 atm, and the mercury level is 115 torrs differences. So you do add them up together. I was all right all the way through this, and I lost my spot halfway down. So, converting this one, for this one, turns into 1.51 atm. And so I added up to the 1 atm. So it becomes 1.151 atm. So that's why I was so confused. I looked halfway down. So sorry about that. Okay, so again, for this one, for 3 sig figs though, remember for addition for the last one, that we want to go, since it started off at 1 atm, now they set it as 1.00 atm, so this is the last place for sig figs. And so that means it has to round for this one. So that's why for the answer turns into 1.15 ATM. Because remember, for addition for sig figs, you go to the last spot for significant figures, not the number. So that's why, because this one is 1.00 ATM is how they give it to you. So you have to round it to the hundredths place as well. Sorry about that. Alright, so if you have any questions, be sure to email me, but I think I fixed it and I think I explained it, re-explaining it to where you know what the proper answer is for this one. So that's the answer for this problem in ATMs. And torrs, it would, and so it just says it just wants it as an ATM, so you don't have to worry about converting back to torrs. Okay. So again, you just take what atmospheres is, convert from the millimeters of mercury or torrs to atmospheres, and then add them up together. Okay, so let's go ahead and let's move on. Alright, so we talked about yesterday introducing into the chapter 5 of gases and with the gas laws. We introduced what a gas is, kind of re-talked about it again. So I'm going to ask a couple of questions so that way you can kind of hopefully think back and remember. Now remember, if you don't remember some of these, you need to write down the term and the definition that you don't know so that way you will use your time properly for it. So think about going through the 5 parts of the kinetic theory of matter. What is one part? There are 5 postulates or 5 parts of it. Alright, hope you remember, okay, gas molecules are in constant rapid motion. What's another part? If you want to cheat and look in your book, you can, but keep in mind, you do need to know these. Gas molecules undergo elastic collisions where they don't lose any energy. The kinetic energy of the gas molecule is directly related to temperature. The gas molecules are very far apart and are negligible in volume compared to the volume of the gas. We're not talking about the individual gas molecule, we're talking about the volume of the whole gas. And the number 5, gas molecules have a negligible attraction between them, to where they have a very slight attraction, but not really. Alright, what do you call a gas that exactly obeys the kinetic theory? So what do you call a gas that obeys the assumptions of the kinetic theory? What do we call it? An ideal gas. Perfect. Alright, so those are kind of the ideas we talked about yesterday. We got into it with gas pressure as well. What is the equation to find the kinetic energy of a substance? I'm going to go ahead and erase this. I'm going to need my board. So kinetic energy, KE equals 1/2 mass times velocity squared. So make a note, that's the equation. What's the equation to find pressure? So P equals force over area. Good job. Alright, so what is the major unit for pressure? Pascal, perfect. Alright, so let's see, what is the device that's used to measure atmospheric pressure? Barometer, that's it. Who invented the barometer? Discovered air pressure. Evangelista Torricelli. So make a note, Torricelli is his last name. So Evangelista. So that's how it looks in English. It's not how you say it in Italian, but that's how it looks. So that's how I'll pronounce it for right now because I can't say his Italian name very well. So Torricelli, make a note for his last name. Let's see. Alright, if I have, let's see, 764, whoops, that is not 760, 760 torr, how many millimeters of mercury do I have? Remember, they are equal. So if I have 760 torr, I have 760 millimeters of mercury. If I have 760 torrs, how many ATMs do I have? Or how much of an ATM do I have? I have 1 ATM, because it takes 760 torrs to equal 1 ATM. What's a device that is used to measure the the pressure of a gas? What's a laboratory device? Manometer. Perfect. Alright, what is, I think that's as far as we got yesterday. So let's finish talking about the manometers, because we have a lot of math to talk about today. So just make a note that I was talking about the kinetic theory with the manometers. So I have these 2 diagrams. We watched one of them yesterday. So for this one, again, it's showing you that they'll open up the gas and the mercury will shift on the inside because it's kind of like a reverse tug of war. So in this picture, which one's stronger? Alright, the gas, because the gas is pushing the mercury towards the atmospheric side. Alright, looking at this one. So again, open to the atmosphere, open up the gas. Which one's stronger? The atmosphere is stronger. So for this type of problem, you would have to subtract how much the mercury moves because the gas is weaker than the atmosphere. Alright, there's one last type of manometer. So let's look at that on page 63. So if you didn't know the terms and definitions, make sure that you note them. You do need to work on them. I know we just introduced them yesterday, but you need to know them. The last one is a closed-end manometer. So for this one, the one we talked about so far is an open-ended manometer. So sometimes they'll have a closed one though, where it's sealed off. So if it's sealed off, can the atmosphere get into the inside of it? No. So this one is a closed manometer. There's no atmosphere pushing on it, so it's outside. So because of that, we don't care what the atmospheric pressure is of this object. We just worried about, okay, how much does the mercury move on the inside? So for this one, they'll just test to see, okay, what's the pressure of the gas? How much is it moving or shifting on the inside of it? The closed-in manometer has a vacuum. Remember, do you remember what a vacuum is? A vacuum, remember, is a space where there is no matter, so there's no air trapped over here either. So the gas, they open it up to see, okay, how much does it move now? And then they'll just say, okay, the strength of the gas is how much the mercury moves. So these are really easy compared to the ones you've been doing. So if it's a closed manometer, they are just indicated by the difference in mercury levels. They don't depend upon the atmospheric pressure. We don't care what the atmosphere is doing because it's already sealed off. So your book points out as the example on the right side of the page on page 63 that if you have the mercury move 350 torrs or 350 millimeters of mercury, if it shifts that much, that's the pressure of the gas. You don't have to worry about doing add or subtract. You just say, okay, if it shifts 350 millimeters of mercury, then it has a pressure of 358 millimeters of mercury or torrs. That's it. So you just see how much it shifts by. So these are really easy, really straightforward. You just see if it's a closed one, if it shifts 23 millimeters of mercury, sorry, it would shift this direction because it's closed. So if it shifts 23 millimeters of mercury, then its pressure is 23 millimeters of mercury or 23 torrs. So you don't have to worry about adding or subtracting. So these are really straightforward. You just see, okay, which direction does it move? And then just record that much, how much it moves by. Alright, well not really which direction it moves because it'll move away from the gas, it's the gas pushing it. But you'll just see how much it moves by and just record that amount. So closed-in manometers are really straightforward. Alright, let's look at the top of the page on page 64. This is where we kind of practiced a little bit. So if you were a little bit confused in the homework, here's some extra practice. So a sample of the gas in a flask is attached to an open-ended manometer. So this one is open-ended. So I'm going to go ahead and reopen up my drawing so it's a little bit easier to see. Oh, I broke the top. So this one is open-ended. For each of the following measurements, determine whether the pressure of the sample gas is greater than, less than, or equal to the atmospheric pressure, and calculate the gas pressure if the atmospheric pressure is 753 torrs. So 753 torrs, that's the atmospheric pressure. I'm going to erase part of these right now. So that's the atmospheric pressure. So it says the mercury level on the atmospheric side is 33 millimeters higher than the level on the flask side. So the mercury level on the atmospheric side is higher. So if it's higher on the atmospheric side, that means the gas is stronger, the atmosphere is stronger. If it's higher on the atmospheric side, alright, it means gas is stronger. So if the atmosphere is 753 torr, and the gas is stronger, should I add or subtract how much it moved by? You should add them up together. So if it was 33 millimeters of mercury, converting to torrs, add them up together. Now this one is 786 torr, so that's the answer for this first practice problem. Alright, letter B, the mercury level on the atmospheric side is 45 millimeters lower than the level on the flask side. Alright, so if it's 45 millimeters lower on the flask side, oops, lower in this direction on the flask side, then which one is stronger? Reading time. The mercury level in the atmosphere, I did read it wrong. The mercury level, I need to stop reading so fast, that's my trouble. The mercury level on the atmospheric side is 45 millimeters lower than on the flask side. So I was right the first time. So it's lower on the atmospheric side. So if it's lower on the atmospheric side, which one's stronger? The atmosphere or the gas? Atmosphere. So for this one, it's 753 torr. Alright, now if the atmosphere is stronger, do I add or subtract how much it moves by? You subtract because the atmosphere is stronger, so it's pushing it down. So I subtract the 45 torr, and I end up with 708 torr. Alright, so that's the answer for part B. Alright, example 5.C. The difference between two mercury levels in a closed-in manometer is 345 millimeters of mercury. What's the pressure of the gas? Alright, if it's a closed-in one and it's not open to the atmosphere, do we care what the atmospheric pressure is? No, we don't care. So because of that, you just look to see how much does it shift by. So it says that it shifted 345 millimeters of mercury. That's a really bad M. So if it shifted 345 millimeters of mercury, how much is that in torques? 345. So 345 torque. So that's the answer for that second example problem. Alright, so hopefully you understand how to work with manometers. I think you have one more homework question, but if you're running into trouble on this, email me so I can help you out with it. But hopefully it's been enough practice to where you get it and you understand. Okay, I know what's happening with it. Alright, let's look at gas pressure and milkshakes really quick. Maybe I would call on one of you to read it, but this is kind of a cool one, so I want to go ahead and talk through it. Have you ever wondered why a liquid which is a soft drink is able to rise up a straw when you suck on it? You do not pull the liquid up the straw by sucking on the straw. Rather than sucking on the straw has one end of the liquid, you reduce the pressure inside the straw to below atmospheric pressure. This action causes the atmospheric pressure from the surface of the liquid outside the straw to be greater than the pressure on the inside of the straw. When the excess pressure inside the straw forces the liquid up into your mouth. Without atmospheric to force the liquid from the region of high pressure to the region of lower pressure, you would not be able to drink the straw. You don't have to create a total vacuum in your mouth to cause the liquid to rise. You merely have to reduce the pressure within the straw enough to balance the weight of the additional liquid in the straw. And then it gives it to you. A reduction in pressure of about 11 torrs is sufficient to cause the beverage in a straw to rise 15 centimeters or about 6 inches to your mouth. Next time you're at your favorite fast food restaurant, drinking a soft drink or a milkshake, remember the atmospheric pressure forces the liquid up into your mouth. A lot of people assume that, okay, if I have a straw, and if I'm drinking the straw, I am sucking or pulling the liquid up to my mouth. That is very hard, and so thankfully it doesn't work that way. So if I have a straw in a beverage, and it's open to the atmosphere is pushing down on it all the time. The atmosphere is pushing down. So if you, and there's even atmosphere on the inside of the straw pushing down on it. Now whenever you put the straw into your mouth and you pull the air inside the straw away, you're reducing that pressure. So you don't have to make a total vacuum. You're just making the pressure inside the straw weaker. And since the pressure on the outside in your beverage is still the same, it's helping you push the liquid up into your mouth. So it's not like you're creating a total vacuum, sucking up the air and sucking up the liquid. You just have to reduce the air pressure enough so that way the pressure outside of it is greater and it'll help push the liquid up to your mouth. Now, you have to use different amounts of air pressure. Sometimes different liquids require more air to be gone for it to rise up in the tube. Like Wendy's Frosties are really thick. Those take a while. You have to remove a lot of the air pressure for the air to, and sometimes you have to just wait just for your frosting to melt for the air pressure to have enough strength to push it up the tube. Now, sometimes this kind of weirds out students, so the easy way to kind of show this, and if you have a beverage and a straw at home, you can do this as well, but you want to make sure you do this over a sink because it kind of has a tendency to make a little bit of a mess. But what I'm going to do, and I'm going to have to talk through to kind of explain what's happening for it, and then I'll have to show you what I'm doing as well. Because I can't talk and do this at the same time. Alright, so this is coffee I decided, because I like coffee, you guys and Jamie understand this already. So what I did was I sucked up the coffee into the straw, and then I put my tongue at the top of the straw to seal off seal off the top of my straw. Now I flipped it upside down. Now I still have it sealed up here. Whoops, this is why you do this over your sink. Now I still have it sealed up here, so that way I have pulled out on the inside of my straw a lot of my air pressure, and I filled it up with liquid on the inside. Whenever I cap my tongue against the top of it, I seal it off at that point. And that's why whenever you flip it upside down, the coffee on the inside isn't falling out. I'll show you what happens whenever I let go at the top. Yeah, this is why you do it over your sink, because it makes a mess. But I'll show you again really quick. So this is why. I did it slower so you can see a little bit better. So once I cap it with my tongue at the top, the air pressure is still on the outside of the straw. And that's why even though whenever you hold it upside down, it doesn't fall, because there's no air pressure pushing down on the inside of the straw, but there is pressure around the straw pushing the air back up. Now, once I reintroduce air pressure at the top, that's why it'll work with gravity at that point and pull it back down. So there's air pressure all around it, but the air pressure is strong enough to keep the molecules of liquid of my coffee on the inside of my straw. Even though gravity wants to pull it down, the air pressure is strong enough to keep it sealed up on the inside. This might splatter again, so I gotta be careful. That's the reason why once I let go at the top again, it re-releases and reintroduces air pressure back into it, so that way it will work with gravity at that point to push down. I'm going to get germ actually, right, because that was gross. But that's the reason why you can drink up a straw and you can drink a fluid, because it's the air pressure that's working with you at that point. And you can do some kind of fun things with straws and air pressure. I'm going to have to clean this up later. So that's one reason why how a straw works. So again, you don't have to know like in detail what's happening for it. That's kind of a fun trick you can do with it. And that's the reason why it works that way. Alright, so let's look at the gas laws properly now. Now keep in mind your book is giving you kind of like a disclaimer that gas laws and the gases, they act a certain way, whether or not we really understand it or not. And kind of like I talked about yesterday, that most gases, they'll act like an ideal gas, but they don't do it all the time, 100% every single day. So scientists know, okay, that the kinetic theory of matter and these gas laws were invented to help explain what we notice that the gases are doing. But the gases are going to do it regardless of whether or not we understand it. This is just our best explanation over how they work, and on most day-to-days, it works out fine. So that's the reasons why we study the kinetic theory with the gases, because the kinetic theory was invented to try to explain why the gases are doing what they're doing, even though even though they don't follow it all the time exactly, it's a best guess situation. So it's one of those, okay, they follow it in most cases, so this works as a good theory. Alright. Your book points out the gas behavior under most normal conditions can be described as simple mathematical relationships. So we have the order and design. Even if it doesn't work out exactly perfect, because you don't understand it exactly all the time, it works out most times. The scientists acknowledge, okay, there's definitely that order and design, even if we don't understand exactly what's going on. Alright, so your book introduces kind of two separate equations and then gives them to you as a combined equation. I'm going to go ahead and just show it to you as a combined equation. This is a good shortcut. So if you want to flip over to page number 68, you'll notice that there is the combined gas law. So it's PV over T equals P2 over T2. So the scientists have taken Charles' law and Boyle's law and have combined them into one equation. If you know this equation, you can find the combined gas laws, Boyle's law, and Charles' law. We'll talk about the reason why. So instead of memorizing three separate equations, you're going to just memorize just this one, but you do want to note what the different laws say. So you can recognize, oh, that's Charles' law, that's Boyle's law, or that's someone else's law. So just think, oh, this is the equation you want to start memorizing. Traditionally, we put it PV first. I've seen people write it as VP over, and then over here, V2, P2. So that way they remember it's vice president in the top. If that works for you, that's fine. But you do need to remember that it's the pressure and the volume in the top over temperature. So your book gives it to you in this format because that's the standard version of doing it. If you flip it to remember that it's vice president or volume and pressure in the top to help you to remember it, that's fine, you're not wrong. But just remember that this is how your book traditionally puts it. Alright, so looking back at Boyle's law. Boyle, what he was working with pressure and volume. So your book has this picture on page 6, well, it has a picture close to this showing you on page 65 what he was doing with mercury, because again, mercury is dangerous, but in this area they didn't really know that well. So they would use mercury to help show different things. So that's what this moving diagram is to help you kind of see for it. That he was having mercury and he would have a section of gas trapped in his tube, and whenever he would increase the pressure, the gas would get pushed closer and closer and closer together. So he was noticing, okay, if I increase the pressure with the mercury trying to spread out, it'll push the gas closer and closer and closer and closer together. Now remember, gases don't like that, so he's having to increase the pressure to push them together. So he was noticing, okay, there's a relationship in between them. If I increase the pressure, the volume has to go down. Your book does not have this diagram, but I like it, so I stole it from physical science. But that's what this diagram is showing you as well, that if you have a gas trapped in a container and you increase the pressure on it, that you're forcing your gas molecules to be together. So if you increase the pressure, the volume has to shrink or be smaller. Now the gases, they don't like that, so they're pushing back. That's why it takes more pressure. Now let's say though that I want to reduce the pressure. If I reduce the pressure, whoa, that is not what I want to do. I'll come back over here. If I reduce the pressure, what's going to happen if I take some weights off because the gas doesn't like being pressed together? They will spread out, or the volume will go up if the pressure decreases. So these two ideas are inversely proportional. If pressure goes up, volume must go down. But if the volume goes down, then the pressure will go up. So these are in inverse proportion. So that's what the book is telling you on page 66. So mark Boyle's law, what it says. Boyle's law, at a constant temperature for a given amount of gas, volume varies inversely with pressure mathematically, and then it shows you that equation. Don't know that equation. That one is, it states the same idea. But the Boyle's law equation is farther down. Now you'll notice that there's kind of this weird fish symbol in the book. That just means it's proportional to. So it's saying the volume is proportional to the inverse of the pressure. Again, you don't need to know it like this. Your book's just pointing it out to you. Now you'll notice it gives you Boyle's law as P1 times V1 equals P2 times V2. You will notice that's the top part of this combined gas law. So it says, at a constant temperature, pressure and volume are inversely proportional. So mathematically, if the bottom denominator of an equation is the same, what do? Right, you can just cancel them out. So if this is 5 degrees Celsius and this is 5 degrees Celsius, you don't have to divide by 5 on one side and divide on the other side. You can just mentally know, oh, well, this is the exact same on either side. I can just cancel them out. I don't have to do anything with them. So yeah, that's the same idea. So if you use the combined gas law, you just make a little note of, okay, I don't worry about the bottom. If it's at a constant temperature, it's not changing, so I don't have to worry about it. I just worry about the top part. The P1 times V1 equals the P2 times V2. That's Boyle's law, but I can just use that part of it. Alright, so let's practice through this. So it says, a flexible helium-filled weather balloon has a volume of 500 liters at a pressure of 1 atm. What will the volume of the balloon be when it reaches an altitude in which the pressure is only 5 atm? Assume temperature is constant. So again, if the temperature is constant, you don't have to worry about the bottom portion, because we're only worried about the top part that's changing. Alright, so it says, for Boyle's law, you want to be careful. I'm going to knock this over. I'm going to move this. Now, remember, for Boyle's law, you want to keep your initial conditions together. Well, all of your laws, actually. You want to keep your initial conditions together and your final conditions together. So if it tells you that the first pressure is 1 atm, you want to make sure you keep that in the front part. So 1 atm, and then the second pressure is 0.5 atm. So it is important that you match them up. If you flip them, it's going to give you the wrong answer. So that's why it's important to know what P1 is, what V1 is. These are your starting conditions. These are your final conditions. So just make a note for that. So I'm starting at 1 atm, and my volume is starting off at 500 liters. So that's my first volume. I don't have to worry about temperature, because temperature is not changing, so we're going to ignore the bottom. So I have to find the second pressure. So this problem is pretty straightforward. So if it's just 1 atm, I'm going to leave up the units, 1 atm times 500 liters will equal, I'm finding P, nope, that's atm, so this is pressure. So 1.5 atm, and I'm finding the second volume. Alright, how do I find this? What do? Right, I gotta get V2 by itself, so I just divide by 0.5 on both sides. So 1 times 500 divided by 0.5, you notice, okay, this is pretty easy. So this is just 1,000 liters. Now, since this one is 1 atm, they're giving you 1 sig fig, because I know this is going to have 1 sig fig down here, so that's okay for it. Remember, these zeros don't count because there is no decimal point. So you'll notice, okay, well this makes sense then. Now if this started off at 1 atm and 500 liters, if the atm was cut in half, so remember they're inversely proportional, if the atm was cut in half, then you would expect the volume to double, and that's what we see. So that worked out well. So you have to kind of logically think through that if you get a weird answer, just think it through. Okay, what should I kind of expect to get this? So this one is 1,000 liters. So let's practice with another one though, just so you get a little bit more practice with this. I'm gonna write in a different color because these colors are kind of throwing me off a little bit. Okay, let's say I start off with 940 for the pressure, and I start off with 2.8 liters. Then it switches to 1,150 torr. For the second pressure, what's the second volume? Now, you might wonder, well, if it's torrs, do I have to convert? No, as long as both sides are the same units, it doesn't matter. It could be torrs, could be ATMs, could be million mercury. It doesn't matter. As long as they're the same on both sides, you don't have to convert. All right, so how do you solve this? So again, this is at a constant temperature, so I don't have to worry about the bottom part. They cancel out. So 940 times 2.8 equals 1,150. And I'm finding the second volume. So again, you just divide by the 1,150. And that gives you, for this problem, it turns into 2.28, and then it keeps going. But keep in mind, you want to have 3 sig figs, so it turns into 2.3 liters. So this one, since this one increased a small amount, from 900 torrs to 1,150 torrs, you would expect the volume to decrease a little bit. And that's what we saw, to where it would decrease a little bit. Alright, so again, if you're having trouble with this, be sure to email me and I'll help you out. Alright, Charles' law. Charles, he was working with volume and temperature. So he was working, trying to see, okay, if I increase the temperature of a substance, does the volume increase and vice versa? So he was working out with the mathematical relationship. Remember points out that Jacques Charles and Joseph Gay-Lussac, both of them were working on it. So Charles gets credit for it though. Just make a note of we call this Charles' law. So Charles and Gay-Lussac. Gay-Lussac has another law that he's known for. So he's not just being gypped. So Charles is known for this law, and Gay-Lussac gets another law. So Charles' law, he was noticing that, okay, if I increase the temperature of a gas, because they have more energy, well then what will the gas want to do? Right, it'll want to spread out. So having this moving diagram for it, you don't have this in your book, but if you increase the temperature of the gas has more energy, so it wants to spread out as much as possible. So he was noticing, okay, if I increase the temperature, the volume also increases. If I decrease the temperature, the volume also decreases. So remember, that's a direct proportion, or it's directly proportional, where what happens to one happens to the other one. So he was noticing, okay, that's kind of weird, and so since he was working with this one, he gets credit for it. So he was noticing, okay, that if I decrease the temperature, because the gas has less energy, it'll also decrease as well. So he was noticing that these are directly proportional to each other. So your book gives you his equation. You'll notice his equation is V1 over T1 equals V2 over T2. That's how come I just gave it to you. It's just combined already. Because for Charles' law, you have to have a constant pressure. You'll notice that the weights in the pincher didn't change. So that the weights are always there. It's just the volume's changing because the temperature is changing. But kind of at the same idea we talked about previously, if this number doesn't change, if the pressure doesn't change, you can just cancel them out or don't worry about them. Because they're not changing, so you can skip that step. So making it, this is Charles' law. Whenever it says pressure and volume, excuse me, not pressure and volume, temperature and volume are directly proportional. You make a note that that's the equation it gives for you on page 67. Now, for this one, you have to solve it on the Kelvin scale. You can't solve it on the Celsius scale. Your book points out that even though you have the degrees in Celsius and the degrees in kelvins are the same length, mathematically, whenever they doubled the temperature in Celsius, like if you went from 30 degrees Celsius to 60 degrees Celsius, they thought that, okay, since the temperature is doubling, my balloon size should also double. But it didn't. So they said, okay, something's weird is happening to this. Let's switch it to Kelvin. So remember, if you're going from Celsius to Kelvin, what do? If you forgot, you need to go back and rework this. So you add 273.15, add them up together. So for this one, 303.15 Kelvin over here. So it'd be 300, adding up 273 to this side as well. That's a really bad plus sign. So for this one, doing quick math, 333.15. I did not work this out ahead of time. Yeah, it should be 333. But they notice, okay, well, it's not really doubling then. So it's increasing, but it's not doubling. So they said, okay, this mathematically works out with what we see, with what's actually happening with the balloons. So that's why you have to use the Kelvin scale with Charles' law. Because if you use the Celsius, it'll create to where it looks like the balloon's supposed to do something, and it's not. So make a note for that one, that your book points out you have to use the Kelvin scale on page 67. When working with relationships of temperature and volume, you must convert Celsius temperatures to an absolute scale, or the Kelvin scale. You have to. If you use it in Celsius, it's going to be wrong. Alright, your book points out though as well that theoretically then, if temperature and volume are directly proportional, if I were to cool down a gas to absolute zero, if I were to take a gas and get it closer to zero, to where it's 0 degrees Kelvin, the coldest possible temperature, what should also theoretically help it happen to the gas if they are directly proportional? Your gas should theoretically condense into nothingness and just disappear, have zero volume. So that's one of those, okay, that's kind of cool on paper. In real life, it doesn't do that. Whenever you cool out a gas that far, it turns back into a liquid and then a solid. So you can't get it in a gas at 0 degrees Kelvin. But in theory, because they are directly related, if you have 0 degrees Kelvin, you should also have 0 degrees volume. But in real life, you can't get it to do that. So just make a note though that your book was out in theory. No substance has 0 volume at 0 degrees Kelvin. Has 0 degree. No substance has 0 volume at 0 Kelvin or at 0. But in theory, you should. All right. So let's work the practice problem at the top of the page 68. So your book points out at a constant pressure that the volume will necessarily decrease and the molecules will cluster together because more collisions will be needed per unit area to maintain the same pressure. So let's practice with this on page 68. A balloon has a volume of 1,000 milliliters at 300 Kelvin. So it's going ahead and giving it to you in Kelvin. Keep in mind though, if you're giving it to you in Celsius, you got to convert. And to convert from Celsius to Kelvin, you got to add 273.15. So make a note for this one. A balloon has a volume of 1,000 milliliters. So 1,000 milliliters at 300 Kelvin. So that's your first temperature. It is placed in a laboratory freezer at a temperature of 200 Kelvin. What is the new volume? Now keep in mind you want to keep your initial conditions together. So this is my first volume. This is my first temperature. Here's my second temperature. I'm finding second volume. It's assumed, since the pressure is not mentioned, that the pressure is the same. Since the pressure isn't mentioned, you can just mentally cancel out the P1 and the P2. So for this problem, it's 1,000 over 300 equals the second volume over 200. All right, how do I solve this? All right, I have to get the V2 by itself. So how do I move the 200? What do I do if it's in the denominator? Right, I just multiply to cancel it out. So 200 times this will cancel that out. So again, order of operations doesn't really matter. So 200 times 1,000 divided by 300, or 1,000 divided by 300 times 200. Whatever it is, doesn't matter, as long as you remember to type it all in correctly for it. All right, so the answer for this one turns into 667 with the 3 sig figs. If you type it into your calculator, I didn't write that one down. Let me punch that one in. So that's the approximation. All right, so 200 times 1,000 divided by 300. All right, you get for this one, let's see. Oh, I only multiplied times 100. 200 times 1,000 divided by 300. All right, so you get 666. Well, that's weird. 666.6666, and that's creepy and weird. All right, so anyway, rounding it to 3 sig figs, it becomes 667. Slightly better number, we would say, as a Christian. So this is milliliters. This is milliliters as well. So that's what the answer turns to. Keep in mind the numbers aren't bad. It's just kind of creepy for Christians. You get a little uneasy around that. All right, so 667 milliliters. Alright, so talking about the combined gas law all together now. Do you know what Charles' law, what Boyle's law says? But as long as you know your combined gas law, you can use this equation to solve any problem. So rather than just memorizing Charles' law and Boyle's law, if you memorize this one equation, it'll save you time because you can just mentally cancel out the others. So this is the combined gas law. This is the equation you do have to know. Do make a note of this on page 68. When solving problems using the gas laws, only the initial and final conditions matter. It doesn't matter what change, it doesn't matter, I'm trying to think, how much it changes in the process. You're only worried about, okay, how much did it change, what did you start with, what did you end up with? That's the only thing that we're concerned about with the gas laws. You don't have to worry about the process. You just look at, where did I start, where did I end, okay, now what happens for it? So that's the only thing that you're worried about for it. So the main thing for this one is you have to make sure that you keep your units matching up. You have to make a note of what is my P1, what is my P2, what is my temperature. In a lot of cases I'll have students write off on the side. So P1, D1, T1, P2, I need to put them in order, B2, T2. So that way it helps them to see, okay, what am I finding? Where am I going for it? Because if you have a complicated problem, like the one I gave you in 5.5, it'll help you to see, okay, what am I starting off with? What am I ending with? And what am I finding? So I would highly recommend that you do your setup like this because it'll help you to figure out what do you need to do and where do you need to go for it. Alright. Okay, we'll go ahead and we'll stop there and we'll practice more with this tomorrow. So your homework for tonight, so go ahead and take out your assignment pad. You're going to finish reading this, so page 68 if you didn't finish it, so read pages 68 through pages 70, so 68 through 70. Alright, you want to answer on page 71, concept reviews 3 and 4, so concept reviews 3 and 4, and then work the application on page 71, 1 and 2. So on page 71, you're doing questions 3 and 4 on the concept review, and the application 1 and 2. Kind of helping you start thinking about it. We'll practice more with the combined gas law and introduce your other laws later. So just make a note though that you want to start trying to think through, okay, what are the steps for it? Alright, you have a good afternoon, and I guess a good morning as well, because it's still morning.